Okay, so I should be going. So today I want to talk about the following theorem. So instead, for every n greater than 4, every smooth hypersurface x of degree n in Pn is birationally super rigid. Okay, so this is a generalization of is a natural generalization of Iskowski-Manning theorem. So the n equal to 4 case, this is Iskowski-Manning, and the key assumption, the key point here is looking at degree n in Pn. It what ensures that the minus kx is isomorphic to OX of 1, and this is by adjunction. So that's the right assumption. That's why we look at this. This is the last degree for which is Fano. If you go 1 degree higher, then it's a Calabi-Yau. So to prove this theorem in higher dimension, so last time we saw the proof in dimension 4. So to prove in higher dimension, we need one more tool. So last time, all we needed was 2 things to understand: multiplicities and log canonical thresholds. But to go higher in higher dimension, then we need one more tool, which is multiplier ideals. So let me start talking about that. So first of all, let me give a definition, and then we'll discuss that. So suppose I start with a pair, XC, where X is a smooth variety, and Z is a sum of ZI. ZI is a Q subscheme, is a Q scheme in X. So all the ZI are proper closed subscheme of X, and CI are the coefficients and the rational numbers. Then the definition here is the following. What is a multiplier ideal? Multiplier ideal shift of the pair. So it's defined as follows. So it's denoted with a Jx comma Z. The definition is the following. You push forward. Let me just write it, and then I comment on that. So you look at the following divisor, ky over x. This is minus the inverse image of Z. And then I take a round up. Okay. So let me comment here. So the first thing is f from y to x is a log resolution of the pair. So this means that the pullback of LZ is it becomes a divisor, a Q divisor, and y is smooth, of course, so it's proper the rational map, and then everything is a supernormal crossing divisor, supernormal crossing. So this means the local equations are monomial. Then ky over x, we already seen this. This is a relative canonical divisor. So this is if you think about being ky minus the pullback of kx, the relative canonical divisor. And then if I have a divisor and I want to define what is the pullback, the round up. So suppose that the I are the reducible components of some Q divisor. The round up by definition is simply the integral divisor when I round up all the coefficients. Similarly, I can also define the round down of the divisor to be the sum where I just round down all the coefficients. Okay, this is the round up. And this is the round down. Okay. Well, the round down does not appear in the definition, but in fact, maybe I can actually do it right here. I can write this also. Sometimes it's convenient to think about this as okay. So just I bring the minus inside and pull it outside if you like, and then a round up gonna go to a round down, of course, when you bring a minus sign. Other questions?
Sorry, I have a question. So this Q variety Z, does it consist of smooth ZIs?
No. The eyes. So the eye.
Just divisors, not smooth.
A close-up scheme. You can think of Z just being a Q divisor. And for most of it, it's totally fine. And in fact, we can always reduce to work with Q divisors.
Okay.
But in the proof, it would be natural to look at subschemes which are not divisors. Like maybe.
And so it's not necessarily of codimension 1.
Not necessarily codimension 1, and we define low discrepancies in this setting as well. So it's not really important. So maybe I can make a comment about this. So these kind of things, these kind of singularities of pairs and so on, they come up in the minimum model program. If you're familiar with that. So when you do a minimum model program, then you typically want to work with divisors. And there is one main reason, which is adjunction. So that you restrict to a component and you apply some induction on dimension. That's a typical base strategy to put statements in.
Yeah, because you can use exact sequences because you're codimension 1, stuff like
that. Correct. And do a lot of numerics on the divisors and so on. But in some other geometric situations, like for instance this one, where you look at the base scheme of a linear system, then it's natural to look at subschemes. And we see with the multiplicity bound that actually sometimes it's useful to look at such scheme which are 0-dimensional. And we're going to see this again today.
Okay, thank you very much. And second thing is, so and this relative canonical divisor is just the co-kernel. So when we pull back, we inject into ky, and then we take the co-kernel. That's ky of x.
Well, so I'm going to come back to this on Thursday. So because x and y are smooth, this is just yeah. So
it's the co-kernel.
Because x is smooth. This is characterized by the following property. Omega y is a pullback of omega x. Tensor or y of ky of x. Okay, so it's a divisor which satisfies this relation. But if x is singular, then this is no longer true. So this is the same thing as saying that this divisor is defined by the Jacobian on this map. Also,
okay.
But if x is singular, then you're really comparing the canonical divisors. And if I use the other thing, there's going to be a different way of measuring discrepancies. I'm going to come back to this on Thursday.
Okay, thank you.
Okay.
So Tommaso, what is f-1 of z? Is the schematic counter image? Or?
Yeah, sorry. Okay, let me actually remind you this. Yeah, so this one, maybe I should say that. So let me maybe erase this part and maybe write it here. So the inverse image of z, by definition, this is this thing. But this is schematic inverse image. Another way of thinking about this is that if I can write this as follows. What you do is that you take the ideal of z, you pull it back to y, and now because there's a log resolution, this becomes locally principal, so you're going to write it in this way. So the schematic inverse image of a scheme is exactly defined this way. You pull back the ideal, and whatever ideal you get upstairs, there's going to be the ideal or the pullback. Now, because there's a log resolution, this is locally principal, so it defines a divisor. So EIs are T divisors. And so that's my notation for f inverse of z.
So, but so if you have a scheme z which is irreducible, right? f-1 of z can be reducible, right?
Oh yeah, typically would be, yeah, because You blow up several times. Just think about the pullback of if Z is a divisor, this is just a pullback of the divisor.
Not the pullback, it's the total transform.
The total transform for a divisor is what we also call a pullback.
Okay, it's the total transform, so it could be non-reduced.
Typically, it will not be reduced. It might have several components because you extract a lot of exceptional divisor.
Right.
It's going to have thickening and all these components. Yeah, it can be very complicated, even if this is a variety.
Sure, sure. So, but when you talk about the roundup.
So the point is that because it's a log resolution, these things become a Q divisor.
Okay, and then you round up the coefficients of the single divisors, right?
Correct. Correct.
Of the single. So, okay, you do not round up only the CI, so to speak.
Well, yeah, exactly. No. I need to do this on the single divisor. This is very important because a roundup is not a multiplicative operation.
Okay, right, okay.
The roundup of twice a number is not twice the roundup of the number.
Okay.
So you need to be careful about that. You need to first compute all the coefficients, and then you round up.
Okay.
Okay. So, so in general, this multiplier idea is a fraction ideal sheaf. So it means that it's not really a sheaf of ideals. It could have a fraction. So it is a, if you like, is a finally generated submodule of the constant sheaf of rational functions. But we can ensure that in fact is an ideal sheaf in a proper sense, so it contains set of X, if this is effective, which means that all the coefficients Ci are greater than 0. And we typically work with effective pairs when you talk about multiplier ideals anyway. Another thing that is not obvious is that the definition is independent of the choice of log resolution F. So this is not obvious. It requires a computation. It's kind of a standard computation. But I'm gonna skip that. So this is a remarks, by the way. The third remark is that you can check. So if X is effective, as we always assume in the future, then you can check that the multiplier ideal of Z is trivial if and only if the pair is KLT. The other condition on log discrepancy has been strictly positive. So I leave it to you to verify this with the roundup. The roundup is going to bring the coefficient, and there's a log discrepancy. So there is a 1, and then the roundup is going to bring anything above 1, but then you subtract 1, you get something effective on top. In particular, the log canonical threshold of a pair can be also equivalently viewed as a supremum for the numbers T, such that the multiplier ideal of X TZ is trivial. Okay. So this, the way I want to think about this formula is that you have pairs, and typically you want pairs with some conditional singularities, like being terminal, canonical, or terminal, and then you get to the log canonical threshold. At the log canonical threshold, then you control any condition coming from log discrepancies, because beyond that, discrepancy will go to -infinity. So the way you want to measure how singular a pair is after that log canonical threshold is that at that point, you're going to pick up a multiplier ideal. And then if the pair is more singular, then just means the multiplier ideal defines a more singular scheme. And we're going to use this in the proof today. So let me see some examples. So maybe you take R to be maybe polynomial ring here. So the first one, if I just pick a function, a polynomial in some value, in fact, a holomorphic function will also do. On Cn. Then I can see the multiplier ideal. This is actually the original definition. I put the ideal to the C. This is simply all the h in all polynomial h, such that when I look at h divided by f, and I take a power 2 here and here divided by 2 to the c, this is locally integrable on Cn. So I can interpret the definition as being an integrability condition on this function. This is a function from Cn into R. Wherever f vanishes, this function will go to infinity, and you just ask her whether the area under the graph is bounded. And if you take C large, then in principle the area will block to infinity too fast. But if I multiply by h, maybe I'm gonna compensate. If h vanishes there, I will actually reduce the area to find a number. So this is also where the word multiplier comes from. The 2 is just because we work with a complex variable. Unit of volume is dz wedge dz bar, and that's where the 2 come from. Anyway, this is an easy computation. And how do you do that? Why do you have this definition with log resolution? A log resolution is just a change of variable in the integral, where now you have a function that you're integrating, it being a monomial up to unit. And then I know how to look at integrability condition for monomials. You separate the variables, and essentially is 1 over x to the p computation. So the second thing that I maybe suppose I have an idea, and suppose this is a monomial. We already have a formula for a log conical threshold, and then we have this more general formula, which says, in this case, the multiplier ideal to a to the c on an. This is ideal generated by the monomials u x to the u, with the condition that u plus e, remember that e is a vector of components 1, lies in the interior of C times the Newton polygon of A. So let me draw a picture for this. So you look in the octant, and suppose that this is C times PA. So what you're going to do is that you have a vector here, E, of components 1, 1. So by using that vector, what I'm going to do is that I'm going to translate everything down by E. You can think about moving U up or moving the polyhedron down. And but then there is the interior part, so I need to remove the boundary, and whatever is inside here. So all the monomials. There are some monomials here, of course, but there might be some other monomial inside here. And all those monomials will be the multiplier here. Because when I translate by E, they're going to land inside. Okay. So this I give a good computational tool for in the monomial case. We're not going to use this one though. I just mentioned it since we'll be talking about monomial ideal. So the main feature of multiplier ideals, and probably what actually motivated the definition in the first place, is native vanishing theorem. So I'm gonna just state it maybe. So here's the theorem. I'm gonna set it for smooth varieties, but it holds more generally. I can allow some singularities, but for simplicity, let me just stick to smooth varieties. Suppose X is a smooth variety, a projective. And suppose I have Z, Cj, Cj, it's an effective Q scheme. Now for every J, I fix a divisor Aj, so this will be a Cartier divisor, such that if I look at the sheaf of this divisor, and I tensor on X, and I tensor by the ideal sheaf of Zj, I want this to be globally generated. Then I fix another Cartier divisor, such that if I look at A minus Kx minus the sum of the Cj Aj, I want this to be Neffen big. Okay. So there are some positivity conditions that I want to impose on A, which are captured in these last two lines of the statement. So A is probably an average, which if Z is just a Q divisor, then I will just say A is a divisor such that A minus K minus Z is Neffen big and be done with that. But it's good to have this condition also of when Z is not a divisor. Okay, and now we come to the statement. Then I look at the cohomology on X of X of A, tensor multiplier ideal for the pair, and this vanishes for I greater than 0. So you want to think of this as a generalization of Karamata Vivek vanishing. So yeah. So if in fact if you take Z to be a divisor, you assume there are simple normal crossing and it is Neffen big. Or just take A such as A minus Z is Neffen big at this point. Then this is just Karamata Vivek vanishing. So the main thing here, I don't want to assume Z to be a simple normal crossing divisor. And the idea is that, I'm not going to write down about the idea is that you take a log resolution to reduce to the Karamata Vivek vanishing. And then you're going to use 3 tools, which is besides Karamata Vivek vanishing, you're going to use projection formula, the array spectral sequence, and some sort of relative vanishing. To deduce the vanishing on X. Okay, let me just leave it at that. In my notes, I sketched the proof with more details, so you can look at the proof there. You see exactly how the reduction works. But the important thing is this. So again, you want to think about this as a correction term. In order to get this vanishing, and I need to put a correction term. This correction term is going to just be a line bundle if if Z is a simple number crossing divisor. But if Z is not a simple number crossing divisor, then in general, this will be an ideal sheaf, which can be more complicated. But this vanishing are actually very useful. For instance, the first applications of this were towards Fujita conjecture, which is a generalization of Radar's theorem. But you really want this kind of vanishing, but maybe multiplier ideals is just the idea of a point to get a global generation, for instance. But maybe leave it at that. So the next thing I want to talk about is one more property of multiplier ideals. This is not as famous as Untitled vanishing. This is kind of a specific to this, to what we need. This is a co-length of multiplier ideals. Okay, so again, this property is very specific of the situation we're going to be in, but it's going to be useful in the proof. So here's a proposition. Suppose I start with X and Z as an effective pair. Where X is smooth, and this time the smooth condition actually is important. Say of dimension n. Now, assume the local-Nichols ratio of the pair is less or equal than 1. So the pair is not Kelty. So in particular, the multiplier ideal is non-trivial. So we're going to let sigma inside X be the scheme. I mean, let it here. So multiplier ideal. It's not trivial. Sigma is a scheme defined by the multiplier ideal. Sorry. No. I'm going to take the thing defined by the multiplier ideal, not of xz, but of x to z. So you notice here, I double the boundary. Okay, think about z as a boundary, and whatever that means, it's just a word. And I double this contribution, so the pair is becoming twice as singular in a certain sense. Okay, and now so at this stage, this only said that this is not trivial, but it could be just defining a reduced point. But if I double, then actually my claim is that in fact the scheme defined by it will be actually very thick if it's zero dimensional, say. In fact, the statement is the following. Then if I look at the length of the structure sheaf of sigma, this is a list, and now this is a strange number, 2 to the n plus n choose 2 times 3 to the n minus 2. Okay, so it seems pretty mysterious, but let's see where these things come from. Okay, so let me just say again what I want to prove here.
Sorry, so this proposition holds only if the support is zero dimensional.
Well, if the support is not zero dimensional, then the length is infinite.
Oh, so obvious. Yeah. Sorry. Thank you.
So, but yeah, I can assume that is zero dimensional.
Zero dimensional, okay.
That's certainly the case that we're gonna run into. We're gonna apply when we actually know that this is zero dimensional. And again, if I don't put the 2, then I might just get a point, which the length is just 1. But if I double the contribution of z, then actually I get something very thick, like a highly non-reduced point.
Okay.
So Okay, so this is proposition. So I'm gonna break this into two lemmas. So we'll start with the first lemma, lemma 1. So I have an effective pair and I have a divisor over X. Then we have that if I look at the law discrepancy of the pair where I put the, so here is using the ideal the ideal notation. So I'm thinking about this. I could write sigma there. So this multiplier ideal of X of 2z in there. So I claim that this is less than twice the law discrepancy of Xc. In particular, we have the following implication that if the pair Xz is not KLT, which is our assumption in the theorem, then the pair with the multiplier ideal is not log canonical. Okay, so this is just an easy computation on discrepancies, on all discrepancies. So let me put some notations. Let me just call J this multiplier ideal. Suppose that E is a divisor on some log resolution, like that. So I got denote by KE the coefficients in E of the relative canonical divisor. I'm going to denote by ZE the coefficient of E of the pullback of Z, so the evaluation of Z. And then I call it JE, the coefficient on E of the pullback of this ideal J. Okay. So by definition, the multiplier ideal is the pullback of what? Let me write it in this way. So I have twice the pair minus a relative canonical divisor with a round down, and I put the minus outside. So what is a push forward over? So I'm thinking about this as being, so in general, let me write this in this way. When you write all the coefficients, so this will be a push forward of minus the sum of some coefficients or some divisors EI, and E is one of them. And the coefficients are exactly 2ZEI minus KEI. Okay, using a similar notation. So what does it mean to belong to a push forward like that? So you look at function in X, and you require then the order of vanishing, when you pull back the function to Y, the order of vanishing along each EI is at least that coefficient. So in particular, if I just test this along the divisor E, I see that the order of vanishing of the elements in J, and therefore this JE, has to be at least the corresponding coefficient along E, which is the round down of 2ZE minus KE. Okay, so that's a rational number. K is an integer, but Z in general is just a rational number, but I round it down. And that number is certainly greater than 2ZE minus KE minus 1. Okay, so when I now look at the discrepancy of XZ or XJ, I have to correct this here in my notes. By definition, this is KE plus 1 minus this JE. But JE is get that number, but here with a negative sign, so it's going to be less than ke plus 1 minus that number, so I'm going to get a 2 ke minus plus 2 minus 2 ze. And this is exactly 2 times the discrepancy of xc. Okay, so this is a pretty elementary property. It just uses the definition, what I mean to be the definition of multiplier ideal as a push forward of one of those ideals of that form. So if you think for a moment, oh no, okay, that's it. Any questions on this one? Now, the second lemma is to use this information to get a bound on length. We already have something in place to do that, which is this inequality that we proved last time. But here we want to do something a little better, at least better for low values of. So we could use to bound length. Could use previous theorem. We say something like the length is greater or equal than something like n to the n over n factorial in this case, using log-Conic ratio 1. But this is strong when n is large, but we can do better for low values, small values of r. And the reason is that the principle of that computation is that here I'm just computing the area inside here. Essentially, that's what the computation does. But when I compute the length, if there are not many points, then maybe there's 3 points in here. Then when I compute the length, I'm actually computing the length of something like this. So there is there is a little bit bigger area, and I'm losing the smaller the points are, which correspond to the smaller log-Conic ratio close to 1. Asymptotically, they are the same, but not asymptotically, I'm losing some numbers. So I want to get a better estimate, and maybe the better estimate is when the length is when n is not too big. But that's where the difference is. Okay, so how do you do that? So let me first take the lemma. Okay, so suppose let me just state it in. Well, let me just say this is maybe some regular local ring. Say dimension of R is at least 2. Maybe I should have mentioned this before also. Let me call it n. Suppose that A inside R is some n prime radio, and the log-Conic ratio of A is less than 1. That's the condition I want to use. So not just C, because if C is very small, then I don't have a good way of improving. But the point is that I'm going to use 1 in the formula, and that's where the computation comes in. Okay, and then I have this following estimate on the length. Okay. Okay, so let me prove this. Or maybe I should give some attribution that I forgot to say. So let me go back. Let me leave it there for a moment. Let me go back to the beginning. So this theorem here, this is a long history. So well, you start with Witkowski-Manning, and then Publikov did a case of dimension 4, and also when X is generic in moduli, general moduli, and then Ochelsov did maybe a couple more dimensional case, and then in a paper with Ian Mustata, we did more low dimensional cases, and eventually I gave the proof of that in the general formulation. But the proof I'm gonna give here has a simplification, and this idea of looking at a better estimate here, this idea comes from work of Zhuang, and then also Collat made some improvement, and this is actually a slight improvement on their bounds. So this is gave a simplification of the proof in the very last part of the proof, and so we're gonna prove the theorem using Zhuang's idea at the end. Okay. So proof. I want to prove this bound on length. So the first thing I want to do is I want to reduce to the monomial case, as we did at the time. And now remember that the condition of local concentration of A being less than 1 is equivalent to the condition that this vector E, which is the vector 1, 1, 1, is not on PA, on the Newton polygon of P. So let me draw a picture. Okay, so I have some. So this is PA. And all I know is that the local concentration is less than 1. So if I write this vector E, it doesn't touch, it stopped just before. I don't know how much before, I don't care. But the Newton polyhedron has convexity, so it's convex. So if I have a point outside this point of coordinate 1, 1, 1, then I can find some plane H which passes to the point, to this point E, but it's disjoint from P of A. Okay, so I'm gonna pick up a plane H, and the equation, a convenient way of writing this equation. So here the coordinates are UI. So a convenient way of writing this equation is that maybe some AI UI equal to the sum of the AI. Because if I plug UI equals to 1, all of them, and then I get an identity. So that's a convenient way of writing this equation. And then I'm gonna call T the set of all points in this quadrant such that AI UI is less or equal in sigma AI. So what T is the area inside here. This is what T is. So let me maybe send this. So T is this area here. Oh. Okay. Now, and what I know is that T intersect PA is empty. So the length of R mod A is at least the cardinality of the lattice point inside T. So you notice that these AI are rational numbers, real numbers. You can assume they're rational numbers, but they're not integer numbers. So I need to be a little bit careful about counting. I know that this point is in there, but what other points are there? Now I see that maybe I made a bit of a mess. So let me see if I can. Yes. So let's remove that. Let's remove this. Okay. T in this area here. So I want to estimate the lattice points inside there. So the first thing I want to do is that I notice that here that you have a, so there is a unit cube, which is contained inside T, right? Okay, so how many points do you see? Well, I see all the points on the unit cube out there. So these are 2 to the n. These are the points on the unit cube. And how about other points? Well, that depends on the inclination of H. For instance, in this picture, H is, this is just a two-dimensional picture, is a very easy situation, but just try to picture this in 4 dimensions. You see this become a real mess. But what you see here, for instance, is that depends on the angle of H. So for instance, if the angle of H is like this, I don't have the next lattice point on this ray, but I have the next lattice point on this ray. So what I see is that either one or the other is going to be in there. There is one particular case in which both of them exactly when the angle is 45, but otherwise maybe I get one or maybe I get the other. So I want to count those points as well, at least a few of them. So what I notice is that I also see that I'm going to get, so for every point U1, UN, some lattice point, such that UI is an element between 0, 1, and 2. So in this case, for instance, I'm looking at the point here. This is the point of coordinate 0, 2. Okay, UI is in there. But I want to make sure that I'm not counting the points in the cube twice. So how do you do that? So then I ask that, and there is this two indexes, J and K, such that if I look at the entries Uj and the entries Uk, it's going to be equal to the set given by 0, 2. So either one is 0 and other is 2, or let's see. So as long as I have this, then either the point U1, UN, or 2 minus U1, 2 minus UN belongs to T. But the question is immediate to see that. So this condition here is just to ensure that I'm not counting points in a unit cube again. So at least one of the entries is 2, no matter what. No matter if you're looking at this guy or this guy, one of the entries is going to be 2. So it's not in a unit cube. But because either one is in T, I know that at least half of the points I'm listing here are going to be in T. So I add what? 1/2 of what? Now, of this half, I need to pick 2 points, the Uj and Uk, two entries. So I have of n, so I can choose 2 of them. And then I need to choose which entry is equal to 0, which entry is equal to 2. So I multiply by 2. And now the remaining n-2 entry, I need to choose a value between 0 and 2, 1 and 2. So this gives me 3 to the n-2. Okay. And this proves the lemma. Because that was exactly our bound. You simplify the 2 and you get, so this is the point in the unit cube, and this is the point like this one. Yeah, we are trying to count. Okay, any questions on this one?
Is this going to be sharp?
No, good question. Absolutely not, because I already know that I also have this other bound right here. I also have this bound. So if n is large, I believe that this grows much faster than this quantity. I hope. So
Yes,
you already
you're
see,
right.
for instance, if n is equal to 2, this is sharp. If n is equal to 3, in fact, already I'm missing a third point. So for instance, at least along one of the axes, there's going to be a point where of coordinate 3, 0, 0, or with the one that enters equal to 3, which I'm not counting here. So, and it's actually going to be a relevant point later. So no, it's definitely not sharp. There is a lot of points, but it's hard to count these points. I did some research, and there are actually formulas that allow you to compute these points, but these formulas are practically unusable, at least to people like me, for people like me. So,
But do you mean to count points in lattices?
exactly, to count lattice points in exactly this region, if you like. I mean, there are more general theorem where you have a general polyhedron in Rn, and you want to count how many lattice points you have the equations for the faces. And associated to the equation, there is some angles that you compute, and but these formulas are just complicated.
There are these error polynomials, right?
Yeah, I know. It's really not my subject.
No,
I just
we
know
can
that.
talk about it.
Eh?
If you want, we can talk about it.
Yeah. But again, I look at some references, and I found a close form, a formula exactly for this. I could not use it.
Oh, really?
Yeah, I could not use it. I mean,
let's have a look at it.
but it's not necessary for me because this bound. I mean, the first bound here takes care of most of the cases, if you like to use that. But in fact, this one suffices, and it takes care of all the low-dimensional cases, and is optimal for the lowest dimensional case I care about.
Ah, cool.
Yeah. So it's yeah. No, but it was interesting because I was not very familiar with this problem of counting lattice points, and then I discovered.
Which seems natural, but it is indeed very difficult.
Complicated, exactly. So, okay. So now we can prove the proposition. Let me recall what the proposition says. So it says the following. So I have a pair with low-conical threshold. The pair is less or equal than 1. And Z is a subscheme defined by the multiplier ideal of twice the pair. Then the length of OZ, of sigma, is at least this number, which is the same number in the lemma. Or we are on an n-dimensional variety, smooth variety. And that's what the statement says. And now we have two lemmas, and the two lemmas is exactly what we need, because lemma 1 implies, because of xz is not KLT, implies that the pair x sigma is not log canonical, so log canonical threshold of x sigma is strictly less than 1. But then I can apply the second lemma, which says in this situation, I have a bound on the length of sigma, which is exactly what's stated. Okay, so it's just the combination of the two lemmas give what we need. Okay, so let me maybe summarize a little bit about what we talked so far. Any questions? Sorry, any more questions on this? Again, so what did we talk about? We talked about multiplier ideals, and then we proved two properties of multiplier ideals. The first one is Nadal vanishing. I again, it takes a little bit of time. If this is the first time you see it, it takes some time to absorb the statement. But for now, they just worry about the conclusion of it. The conclusion is that you get some vanishing cohomology where you look at some line bundles on your variety, sufficiently positive, kind of adjoint line bundle because of this kx appearing right here. And then you twist by some multiplier ideal, and you get zero high cohomologies. And the second thing we proved about on some of this on how singular this multiplier ideal can be in a particular situation. And the idea is that I want to contrast these two informations. The proof will be a combination of these two theorems. Vanishing theorems is going to give me an upper bound on the length of a zero-dimensional scheme using cohomology. But then we have this local computation and give me a lower bound. And then we show that, in fact, the two contradict each other. OK, so now I can prove the theorem. .4. Now we talk about birational rigidity. Again, the theorem I'm going to prove, as I said at the beginning, is the following. For every n greater than 4, every smooth hypersurface of degree n in Pn, birationally superrigid. Okay. So proof is that first we already observe that kx is linearly equivalent to Ox of 1, is by adjunction. And another thing that I want to say is that the Picard group of X is generated by the plane section, or the canonical class, if you like. This followed by Lefschetz theorem, Lefschetz hyperplane theorem. Here we're using the dimension of X is at least 3. So now assume X is not birationally superrigid. So then we apply the Noether-Feynman inequality. Implies that there exists a movable. If you can find a movable, boy. A movable linear system H inside some multiple by Lefschetz, right? Some multiple of the hyperplane class, which is the same thing as a multiple anti-canonical class, such that for a general element D inside H, the pair X 1 over RD is not canonical. Okay, so the singularity. That was the Noether-Feynman inequality if you start with a Feynman manifold of Picard number 1. But then we have some information on the multiplicity of these divisors. So if you use Publikov bound or multiplicity, the first one, the easy one, it says that the multiplicity of D along C, any curve, is at most R for any curve C inside X. So when I now rescale it by R, I get this Q divisor, which has a multiplicity less than or equal than 1. And this says that this pair is canonical in dimension 1. So it's canonical away from a finite set. So the pair is not canonical, but it's canonical away from a finite set. So this implies, so therefore, there is some divisor E over X with center a point P inside X such that the discrepancy, low discrepancy along D is less than 1. Okay. So that's what it means. So the condition on low discrepancy being less than 1, I said. Less than 1. The condition on the low discrepancy being less than 1 is another way of saying that the pair is not canonical. But the fact that the center is at point P, this is forced by the fact that the pair is canonical in dimension 1. It's canonical away from a finite set. Okay. So what I'm going to do now is I'm going to fix, it's convenient, I fix a numbers, a coefficient C slightly smaller than R, such that AE of X CD is less or 1 or less or equal than 1. For instance, I can take C to be the canonical threshold. I didn't define the canonical threshold, but I think you can guess the definition. And in which case I will get it, maybe I will have equal to 1. But I want to use the fact that C is less than 1 over R. Okay, next thing I want to do is that I want to replace D now by a dimension 2 subscheme. So now let Z be the intersection between two general members. So what is this? This is a complete intersection in X of codimension 2. And what you have is that I can replace D by Z because I can think of D being defined by a general linear combination of the generators of the deal of Z, so the evaluation will be the same. So I still have this condition where I replace D by Z, but somehow it's actually useful to work with this codimension 2 subscheme. Okay, there is more information. Somehow, the point is that the important point here is that when you study this kind of problems, understanding singularity of rational maps, you want to look at a linear system which are movable. And the reason they are movable is because in the terminaces of the map are in codimension 2. So you can remove the any codimension 1 fixed part in the linear system. So we need to exploit that. That's the point. And this is what we're going to do next. We did already in the Skorsky-Mining theorem, we already used Z in an essential way. Okay, so the point is that we have the second bound by Publikov here. It says the following. So if I look at the dimension of the point X inside X, such that EX of Z is greater than R squared, then this is dimension less than 1. So the Z is cut out by two equations of degree R, two forms of degree R on X. And then we have this multiplicity bound of, that says that then the multiplicity along the surfaces of this subscheme will be bounded by R squared. And therefore the set where the bound fails is a dimensional at most 1. Okay, now we are ready to take a, so far this is no different from the proof of Skorsky-Mining. And the next step is also the same. So now the next step is it cut down. So we're gonna pick a general hyperplane section through P. So point P belongs to X. I'm gonna pick up Y inside X. So Y is a general hyperplane section. So what is Y in particular is a smooth degree n hypersurface in Pn-1. So if I use a junction now, you see that this is actually trivial. So it is no longer a Fano variety, now it's a Calabi-Yau manifold. But what you notice is that because P is in Y, this implies that the order, the order along E of the pair X CZ plus Y is less or equal than 0, because I subtract at least 1. The order of Y along the divisor is at least 1. So and now we can apply a junction, and it shows that there is some divisor F over Y. The center P, one can check that by all the information we have, such that the dot discrepancy on the restricted pair this is by inversion of a junction. Okay. So if n is equal to 4, this is the Skorsky-Mining theorem, and we conclude by the bound, the first bound of multiplicity and Bezout theorem. So the key point here is that we had this 4, which was two things. 4 was 2 square, that was coming from the bound, but was also the degree of X in this case. So that's why it works, right? But if n is equal to 5, then I have 2 square, which is less than the degree of X. So this is not enough. So we need to do a little bit more work to get there. You don't get a contradiction from Bezout. Okay, so instead, we're going to prove the following claim. Okay, I write it here. If I look at the pair where double, so I know that the pair, so we know that this pair X C0, sorry. Again, come on. We know that the pair Y, C0 related to Y is not KLT, but is KLT in dimension 1. Okay, so the point where it's not KLT is 0 dimensional. Well, the point is it's true even if I double the boundary. Okay, and this is also so in spite of the fact that we make it more singular, you still have the fact that the singularity is really concentrated in dimension 0. So let's prove this claim. Okay, so by cutting down, we can ensure that a set of multiplicity of high multiplicity also get cut down. So we have the following. This is maybe not completely trivial, but it's true. This set is actually dimension of this set is less or equal than 0. In fact, it's actually dimension 0. So I'm gonna pick, so maybe write it this way. So there exists an open set U inside Y, which is a complement to a finite set such that EQ of this scheme is less or equal than R squared for every Q in U. Okay, just avoid the blockers of high multiplicity, and that has to be finite dimensional. So it's a finite set. Now for every Q in U, I'm gonna pick, so a point Q in U and inside Y, I'm gonna take a surface inside Y. So this is just a general complete intersection surface. So Q. So I cut down to a surface. And what we know is that by doing this generically, is that a question? No. By cutting down generically, I preserve multiplicities. So I know that we still have this bound. But now this scheme here is zero dimensional. And is a complete intersection. So what I see is that, so this implies that the multiplicity of this scheme is the same thing as the multiplicity of the ideal of this scheme in the local ring of SSQ. But we have a bound for that multiplicity. So this implies the local Nichols threshold of S 0 to S, this is greater or equal than what? 2 over the square root of this multiplicity. This is from the formula we proved last time, where I take square roots everywhere. But now, because of our bound of multiplicity, this is greater than 2 over R, which is equal to, which is strictly greater than 2C. So this implies that the pair S, so it's a 2C0 to S is KLT near or RQ. And now by adjunction, in fact, this implies the pair Y. So by measure of adjunction, 2C0 to Y is KLT near Q. So this proved the claim. I also proved that this pair is KLT at every point Q in U, and U is a complement of a finite set. So this means that it's KLT in dimension 1. Another way of saying this is that the multiplier ideal defined by this pair is zero dimensional. And now we are at the last step of the proof. So we see that the multiplier ideal, in fact, it's not on X, but it's on Y. Defines a zero-dimensional scheme. Sigma inside X. Okay, and now we are ready to compute the lengths, to estimate the lengths of the scheme in two different ways. So now we estimate the length in two different ways. So the first way is we're going to use another vanishing. So on y, remember that ky is trivial, and z is cut out by equations of degree r, and c is less than 1 over r. Okay, so what I see here is that the following sheaf OY of 2 will satisfy, because OY of 2, so I don't need to worry about KY because that's trivial. And OY of 2 will satisfy exactly the condition in natural vanishing, because the way you want to think about this, pretend for a moment that this is just a divisor, and then this is a divisor cut out by an equation of degree less than, a Q divisor cut out by an equation of degree less than 2. So if I add 2 to it, I get something F and big, for example. So I get the vanishing of this ideal. Which is multiplier ideal, which is the same thing as ideal of sigma. Okay, so what does it mean? It means that I have a surjection from H0 of y or y of 2 by the exact sequence, so subject on H0 of O sigma. Okay, but now the point is that I don't put a 2 because this is zero-dimensional scheme. So any line bundle will restrict to the trivial line bundle on sig. So this is why I care about ensuring that this is a zero-dimensional scheme. But now what do we know? So this guy is the dimension is equal to the length of O sigma. This guy instead, the dimension, well, this is the same thing as the dimension on the projective space in which it lives. So this is PA minus 1 of O2, just because y has degree larger than 2, so there are no form addition on y of degree 2. And these numbers is equal to n plus 1 choose 2. So what we get here by the surjection is that the length of O sigma is at most this binomial number, n plus 1 choose 2. Okay, so this is where we use the first ingredient, which is narrow vanishing. And now that ingredient is that we use by the previous proposition, we have an upper bound, an lower bound, sorry. So now remember that now n here will be the dimension of y, which is n minus 2, capital N minus 2. So the bound was 2 to the little n, which is 2 to the n minus 2, plus n minus 2 choose 2 times 3 to the n minus 2. So this we get.
Tommaso,
Yes.
is it an equality or a bound? Or...
At least.
Oh, yes, yeah, thank you.
Okay.
Yeah, this is a lower bound. So if you compare these two bounds and you want to have a number in between, then you see that n cannot be larger than 4. It's an integer number. So you get a contradiction as soon as n is greater than 5. So the case of dimension 4, we already settled. And this argument will cover all remaining cases. So this finishes the proof of this theorem. Again, this proof of this theorem has a long history. So Yeah, any questions on this? So that's about this theorem. Let me just, yeah, this theorem here. There is an excellent survey by Collard on the history of this theorem as well that I recommend. So the proof, again, has many stages in which it kind of developed. There were some faulty proofs in the literature, one by me. And so and the proof given here, again, apply the simplification by Zhuang. When Zhuang did this bound, so where is it? So he really didn't really do all the cases. So maybe Zhuang did only look at this bound, and it took care of most cases, or just maybe 5 or 6, maybe 3 or 4 dimensional cases below that are not covered. Then Collard observed that one can improve this bound by counting this type of points, but his bound was 1/2 of 3 to the n. And so this one is slightly better, and the advantage of that is also covered the case of dimension 5. Otherwise, one would have to rely on different proofs, a bit annoying for that case. Okay, so any questions?
When you proved before this simplification, you use the same way the length or some other stuff to get.
Okay, that's a good question. That's a good question. So the proof is exactly the same all the way. Okay, we draw a line. So this is where my proof, where the original proof ended.
Vanishing, okay.
And then in order to get a contradiction, I didn't think of doing that computation. This computation on the law discrepancy or looking at local reconstruction multiplier ideal, that's really an idea of Zhuang, which is actually very nice. And I wish I thought about that, because the key point was try to reduce to the local reconstruction of n primary ideal. And that was in my mind since the beginning. But the way I did it was different. It was a bit more complicated. The idea is that you want to understand what happened. You have this adjunction. The inversion of adjunction is a key statement here. So it goes from canonical to log canonical, sort of in the hierarchy of singularities. And what I've been trying to do for years was to go beyond that. And we say, if I keep cutting down, how do I measure that? And the idea is that you should be able to measure it with multiplier ideals. But the problem is that a multiplier ideal can be thought as being a non-effective pair. If you guys know what I'm talking about, in any case, it's a setting in which inversion of adjunction does not work in the usual way. And so it becomes very tricky to understand what happened. So eventually, one way of doing that was to say, okay, I have this divisor computing some singularities. And then I have 2 things. One is how much my scheme vanishes over there. And then I have also how much the point vanishes over there, because that vanishing of the point is what determines what happens when you start cutting down. And so I was looking at the ratio between these 2 vanishing numbers. If the ratio was large, I would argue in a certain way. If the ratio was small, I would get a contradiction in a different way. So it's a bit more complicated than the end part. So definitely this thinking about improving the bounds and on the length of the scheme in this way, that definitely made this proof a lot nicer.
Gilberto was asking a question.
Yeah.
Oh, mine was more general. So the idea is always the same, that you try to understand the singularities of the base locus, or am I?
Yeah, that's correct.
That's correct. And to understand them, you introduce multiplier ideals in this case, right?
Correct. So yeah. So
Okay.
again, the point is that in degree 4, we had the numbers matching perfectly to get this contradiction using the Bezout theorem.
Yeah.
This high dimension, the Bezout theorem does not apply because the degrees are off. On the other hand, I want to use the information that I'm on a bigger dimensional space somehow.
Okay.
And this is where this bound on the multiplicity comes in. So the point is that, again, Bezout is being replaced in a way by this nether vanishing. There's another way of seeing how the degrees of the equations involve the degree of x and the fact that the degree of the scheme, how this degree control the singularities from above, limit the singularity. So this bound here can be thought as a way of saying it cannot be too singular.
Cannot be too singular.
But then at the same time, because you get something which is not KLT on something on a certain dimension, if you can show that you get something 0-dimensional, and this is what the multiplier reveal does, then you can argue that in fact the singularity cannot be too small, and that's the bound.
Okay, thank you a lot.
So Tommaso,
Yes.
Is there any hope of getting some result for complete intersections?
Yes. So I think you already mentioned this. So these techniques can be extended to complete intersections, but there is a price to pay. So the main price to pay is extending the multiplicity bound of Kubikov. So in order to do that, you have a bound. You say the multiplicity cannot be too large, but the dimension of that locus, you need to allow bigger dimensions. The idea is that essentially to compensate for the fact that you are taking a complete intersection of higher dimension. So all the numbers, all the dimensions of these things will be larger because you need to argue inductively on the equation cutting out the override. So this results in the fact that in order to get to something 0-dimensional, you need to cut down further, more times. So you need more rooms between these numbers. The upshot is that you get results if the dimensions are large enough compared to the codimensions. So you don't get, this is not an efficient way of doing things, for instance, for low-dimensional examples. Like I think we talked about the complete intersection 2, 3 in P5. So in general, if you have low-dimensional things, then there's not enough room to do that. But if you allow for bigger dimensions, then you get some same results.
So who did this?
So this one, yes, let me write it here. So I think that the main paper here to look at is this Fumiaki, Suzuki. So here I find this clever way of extending again, you want to assume again that X is a fan of index 1. This is always there. There's a condition. It's very hard to get away with because another part coming from the notifier inequality, there are two numbers they want you to match. This R somehow has two meanings for us. So the results when the dimension of X is large compared to the codimension. in the projective space. Yeah. So another thing that there are results is when X is singular. And in fact, some of the questions that Ciro, you were asking last time for, so it got me thinking that maybe there is a way of improving some of the results. I want to, next time I wanted to talk a little bit about hypersurveys with ordinary double points.
Mhm.
And so maybe I'll talk about this a little bit next time. Other questions? Okay, so maybe you should stop the recording.
Recording.